If you have any base b and you raise it to any natural number, all exponentiation means is iterated multiplication. B to the n is b times dot, 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 times b, and how many are written down? N of them. That pen just broke. So that's fair enough. What about negative powers? That's what 3 to the 4 means. What should 3 to the negative 4 mean? Oh, I'm off the screen. If 3 to the 4 means 3 times 3 times 3 times 3, what should 3 to the negative 4 mean? It's like the opposite of multiplying by a number a bunch of times. Divide. 3 to the negative 4 just means divide by 3 that many times. And there are two different ways of writing that. That's either 1 over 3 times 1 over 3 times 1 over 3 times 1 over 3. Or, could I like combine all those denominators together? Yeah, that's how fraction multiplication works. 1 over 3 times 3 times 3 times 3. Oh, so you could actually just write that as 1 over 3 to the 4. So whenever you're thinking about negative powers, just think about division instead of multiplication. B to the negative n is 1 over b times b times b times b n times, also known as 1 over b to the n. B to the negative n is 1 over b to the n. People with me so far? All right. So to get positive powers of b, you take 1 and multiply by b that many times. To get b to a negative power, you start with 1 and then you divide by b that many times. What should b to the 0 be? I think just 1? You start with 1 and multiply by b no times. You still have 1? Nice. Anything raised to the power 0 is 1 with a caveat. Oh, right, that highlighter just blacks things out. Provided that the base is not 0. 0 to the 0 is not something that you're allowed to talk about. 0 to the 0 does not technically make sense. In that, depending on how you think of it, you could justify 0 to the 0 being absolutely any number you want. So, we just won't. Well, now we know how to take b and raise it to any natural number power. What about a rational number power? Let's try to make sense of things like b to the p over q. Actually, let's start with 8 to the 1 over 3. So raising something to the third power is like cubing, right? So raising to the 1 over 3 should be the opposite of cubing. Do we already have a name for the opposite of cubing? What undoes cubing? Cuboids. Whenever you see 1 over a number, and that's a thing you want to take the cube root of that base, and in this case, we actually know the cube root of 8 is 2. Whenever you see b to the 1 over q, what you want is the qth root of that base. So if that's what 1 over q should do, then I guess p over q, well, that would be like taking the qth root and then raising it to the pth power. Yeah. And this is maybe getting to the state of technical enunciating that often we'll have to resort to a calculator if we want to actually compute the things. Or like if I have to take the 5th root of 10 to write something down, I don't have any good tools. I know the 5th root of 10 should be somewhere between 1 and 2. That's kind of as good as I. Well, b to the p over q is take the qth root of b and then raise that to the pth power. Again, provided that b is bigger than 0. If you try to do that to a negative power, you might accidentally take the square root of a negative. We feel good right now? So let's just use these ideas to make some computations. What's 2 cubed? Right here on 8? Yeah, because it's 2 times 2 times 2. 8. 4 to the power of negative 3. Well, at the very least, we could write it down as 1 over whatever 4 times 4 times 4 is, right? Let's start with that. We don't need to, like, do everything at once. And in some sense, that's a good enough answer. That's an answer that demonstrates the ideas we have. What is 4 times 4 times 4?
64.
I hear 64. We agree? Nice. And if that's the type of multiplication you need to like go off to the side and actually write down the multiplication to do, great. Maybe our powers of 2 memorized, maybe not. Fractional powers. 8 to the 5 over 3. Let's try to compute that. So by these instructions, step 1 is take the cube root of 8. Take the cube root of 8. And then I need to raise that to the 5th power. So far, so good? Do we know a cube root for 8? 2. So this should be the same thing as 2 to the power 5. So that'll be 2 times 2, 5 times. What is 2 to the 5th?
32.
And here are 32. We agree? Nice. All right, so here's one type of thing that we haven't talked about whatsoever. Is every number a rational number? So you might find yourself in a situation where the thing in the exponent isn't rational, so you can't think of it as taking like cube roots or anything. And really what you want to define something like e to the square root of 2 is as, well, if you take like the first 100 digits of the square root of 2, that's a rational number, right, because it dominates. So you could use this definition. You just have to start by taking like the 10 to the 10,000th root of e, and then you raise it to a big power. Does that sound like awful? And even for a computer, awful. Like things are going to go wrong immediately if that's the definition you use in a computer. So really, what the computer is going to do is it's going to use some ideas from calculus called Taylor series to compute high order exponentials. And for now, let's just black box that. If we want to compute something like e to the square root of 2, let's compute something like e raised to the square root of 2. E raised to the square root of 2. Somewhere around 4.11. And there's an important mathematical note about this number e. That number e is so-called Euler's number. It's the base of what gets called the natural exponential. And there's an exploration of what's so natural about it in the extra credit at the end of the section. The idea is that exponentials are things that grow faster when they're bigger. The growth rate of an exponential is basically the same as the size of that exponential. E has the property that its growth rate is e to the x has the property that its growth rate is exactly equal to e to the x. That's what makes it so special. For any other exponential, there's some like off by a constant. Anyway, let's carry on. So we have this idea of what exponentials are. They're the things you get by iterated multiplication. Let's try to graph them. Let's start with the graph. Let's try to graph 2 to the x. And this graph is set up just right so that the thing will actually fit. Let's plug in some points and go from there. What's 2 to the power 0? 1. So what point should I label on this graph? 0, 1. Input of 0 goes to output of 1. 2 to the 0 is 1. And maybe how low down that is on the graph gives you an idea of how big these numbers are going to get. So let's start going to the left and to the right and see how things grow and shrink. Positive power is positive. What's 2 to the 1? 2. So I guess I better highlight 1, 2. 2 to the 2. 2 to the 3. Finally, 2 to the 4th is 16, 8, 9, 10, 11, 12, 13, 14, 15, 16. So maybe you're noticing something about the height that is like exactly what 2 to the x should do. The height is doubling every time you go to the right by 1, which makes sense. That's exactly what multiplying by 2 means. Negative power. So what's 2 to the negative 1? 1 over 2, or maybe 0.5 if you like decimals. 2 to the negative 2. That's about a quarter. 2 to the negative 3. 1 over 8. Oh gosh, and that's 0.125 if I'm right. Yeah, divide that by 2, you get that. 2 to the negative 4. 1 over 16. And I think we're getting to the point where I can't distinguish between those numbers and 0. So to interpolate between, let's just interpolate between. 2 to the x. Its graph looks something like this. So there's like more time in these notes explicitly on graphing things in a moment, but take a look at that. What are some things you notice about that function? Doesn't touch the x-axis. No x-intercept. What else do you notice? Even or odd or neither? Neither. Does it have any vertical asymptotes? Does it have any asymptotes whatsoever? I think it's got an asymptote of y equals 0, right? It's getting really close to that x-axis, at least when x is really, really extremely negative. And it's like a different kind of horizontal asymptote than you see for like rational functions, right? Rational functions, they always have the same horizontal asymptote as you go to the left and you go to the right. Exponentials don't have that behavior. An exponential will get small on one side and big on the other. Which I guess makes sense because you're dividing a bunch on one side and you're multiplying by a bunch on the other. That feel good? Seems sensible? Nice. How do you think this would change much if I replace that 2 with like a 3? Qualitatively, I don't think so. I think it'd be like taller where it's tall and shorter where it's short, but otherwise I think it'd look about the same. And we'll see that explored a little bit on the next page. All right, so we have this graphical analytic tool that we can use. Let's also develop some algebra. And to do that, let's start with just like a single demo to see a phenomenon. Let's write out 4 to the 7 times 4 to the 2 and see what we get. So 4 to the 7, all that means is I'm going to color code. 4 times 4, 7 times. So 2, 3, 4, 5, 6, 7. There's 4 to the 7. Then I need to multiply that by 4 squared. That expanded correctly? Do those parentheses actually matter? No, multiplication is associative, which is just a fancy way of saying if you only see multiplication, you don't need the parentheses. So how many 4s do you see written down right there? 9. So it's a simpler way of writing that. 4 to the 9. And I certainly don't want to try to expand out what number that is as like its digits, because I don't care. It's probably pretty big. Do you think I could do that for just any time you multiply together two exponentials? Yeah, whenever you have b to the x and you multiply it by b to the y, you will always get b to the x plus y. And I'm putting here this reminder. You better be walking with a base that's positive. If you're walking with a negative base, then you're in a weird situation. You might accidentally like ask what's negative 5 to the 1/2, and then you need a square root of negative 5. It's even worse if you try to like take an irrational power of a negative. Then you really have to walk to make sense of it. So whenever you multiply exponentials, you add the things in the exponent. So tell me, what is 3 to the 3 halves times 3 to the 5 halves? 3 to the 8 halves. And maybe I'll even write the intervening step because I've given myself a luxurious amount of space here. That's 3 to the 3 halves plus 5 halves. And indeed, that's 3 to the 8 over 2. That's something we can keep on simplifying? Yeah, what's 8 halves? Yeah, but say it louder. Yeah, so it's 3 to the 4. Oh, cool. That's not even like so annoying a number to compute. Let's actually write out what 3 to the 4th is. That's 3 times 3 times 3 times 3. Maybe I'll gather together some 3's. Each of those pairs of 3's, what are they equal to? 9. So this is 9 by 9, also known as 81. Cool. So here's the takeaway. 3 to the 3 halves and 3 to the 5 halves, those are things that I would not be able to compute on my own. One of them would be the square root of 3 and then you cube it. Or maybe you could write it down as like 9 times the square root of 3. 3 times the square root of 3? No, 9 times. 3 times the square root of 3. The other one would be something like 9 times the square root of 3. So you can't compute either of those two things without a calculator. But you can compute their product just fine. Their product is 4. And that's something you can do with these algebraic exponential laws. Here's the next one I want to develop. What happens when you exponentiate an exponential? And to get some idea of how to do that, let's use the same ideas. Exponentiation means iterated multiplication. So let's write this down as a bunch of iterated multiplication. 5 to the 3, parentheses, parentheses, to the 4. Well, 5 to the 3 is just 3 5s written down. So this is 5 times 5 times 5. But then I need to do that 4 times. Times. 5 by 5 by 5. 5 by 5 by 5. 5, 5, 5. Spacing isn't actually, that's okay. So I haven't really tried to do the dots before you know where they go. Those parentheses actually matter? Nope, multiplication is associated. How many 5s are there written down? 12. And in particular, 4 groups of 3 5s. That means 3 times 4. basically for anything. Yeah. Whenever you have a positive base, a legal base, and you have some numbers x and y that you want to exponentiate by, b to the x to the y is the same as b to the x times y. And as an aside, something that's useful about that, does it matter what order you multiply those x and y in? No. So that must mean it doesn't matter what order the x and y in want to begin with. It's an ideal worth keeping track of. If you decide it'd be easier to do these exponentiations in the opposite order, do them in the opposite order. Let's also use it to play the same game where we take something that we couldn't compute directly and turn it into something we can compute directly. That look like, well, this looks like something you could apply that idea to. Cool, do it. Tell me what you get. And I am glad that I am not seeing anyone reach for a calculator, because that's the whole point of this exercise. That you don't need it. I guess you can use it to check. What'd you get? Oh, should I talk to him? Ah, okay. Then what'd you get? Right here at 27. Right here a second for 27. Cool. With that written down, demand I talk to him? Okay, then we will do. So, I see a base to a power to a power. Whenever you see a base to a power, and then you raise that to a power, you can just multiply the things in the powers, the things in the exponents. This is the same thing as 3 raised to the 9/2 multiplied by 2 thirds. And now let's look at that. 9/2 times 2/3. Is that a fraction that simplifies? Yeah, at the very least, you see the 2's cancel, right? This will be 3 to the power 9 times 2/2 times 3. The 2's cancel. 9 and 3, do those have any common factors? What is 9 divided by 3? 3. So that's the same as 3 to the 3. Let's see, 3 times 3 is 9, 9 times 3 is 27. And you know what? As long as we are talking about this idea that even on problems that you can just do by hand, and that I want you to do by hand, you can also take a moment and see if you've done things correctly. Let's also use a calculator. Let's compute. 3 raised to the 9/2. And now I need to raise that to the 2/3. And those parentheses that I put there, those do matter, right? You really want to start by doing 9 divided by 2, then raise that to the third power, then do 2/3, then raise whatever the first thing is to that. And indeed, it looks like 27. Cool. So you can use these algebraic laws to simplify exponentials. And what we saw here is you can turn something that 3 to the 9/2, again, you can't compute that directly. that. So it's something that's going to involve a square root of 3. But suddenly it becomes something you can directly compute just by using exponential laws. Another thing that it's useful for is solving equations. I saw that 4 to the x equals 32 is an equation that we can solve. And how will I solve this? Let's use this idea of a power to a power is the same as multiplying in the power. And I don't see that in sight right now. But I do see something. 32, is that a power of 2? What is 32 as a power of 2? 2 to the power of 5. So that's 2 to the power of 5. 4, is that a power of 2? Yeah, it's 2 to the 2. So let's use that. 2 to the 2 raised to the x is equal to 2 to the 5th. That's exactly the same as the equation that I started with. Now so you see a place where you could maybe use this idea of a power raised to a power? Let's use that. 2 to the 2 to the x, how does that simplify? I could rewrite that as 2 raised to the power 2x. Nice. So this is going to become semicolon 2 raised to the 2x equals 2 to the power 5. So I want a number x so that 2 raised to double that number is the same as 2 raised to the 5th power. And let's start by just looking for commonalities on both sides. They both look like they're power of 2. Let's go back to this graph. What are some words that you might use, other words you might attach to that graph? Is it 1-to-1? Passes the horizontal line test. And the whole point of the horizontal line test is it tells you whenever you want to solve an equation, that equation will have either 0 or 1 solutions. Each place where a horizontal line crosses a graph solves an equation. So, the only way 2 to the 2x can be the same as 2 to the 5th is if the things in the exponents are the same, because exponentiation is 1-to-1. So that means 2x equals 5. If you have the same base on either side of an equal sign, you can get rid of the base, because exponentiation is 1-to-1. Oh, does that look like an easy equation to solve now? What's the solution? Five over 2 or 2.5, whichever you prefer. I don't like that or there. There should just be an equal sign between, because they're the same. That feel pretty good? So if you have an equation involving exponentials, but everything seems to secretly involve the same base, use that. And then use the fact that exponentiation is 1-to-1 to get rid of the exponential. Write down a simpler equation. Think you could do something similar for this next problem that's written down? 9 to the x equals 27. So I think here's what I'll do. Either I'll pause for a bit, you'll tell me what the solution is. Then we'll go and check these by doing a few things and see what we wind up with. People feel comfortable that they know how to start on that next one? Anyone, no idea where to begin? Want me to write some stuff? Okay, then I will pause until someone tells me what is the solution to this equation. what you get. You have 3 over 2. Right here a second. All right. Is there a dimension off to it? Cool. So, 3 over 2, or if you like decimals, 1.5. Well, then maybe instead of talking through it, let's think about how you might check that. What's some stuff you could do to check that? Let's plug that in for the x, see what we get. 9 raised to the power 1.5 had better be 32. 9 raised to the 1.5 had better be, nope, 27. Cool, so that checks out. Let's also just remind ourselves, you can look at a graph and read off solutions, right? Let's go ahead and graph 9 to the x. B equals 9. There's the graph of 9 to the x. Let's add in there the line y equals 27. Those things cross at x equals 1.5. So just remember, you can also do things graphically to check. How about that equation? 5 to the x equals 7. Is there a common base between those that you could use to run this algorithm? No. I mean, kind of there is, but finding that common base is going to require the tools we would use to solve that equation anyway. Maybe I'll just point this out. 5 to the x, 5 to the x. The base is 5. Hold on that. Does that look like a one-to-one function? So does it have an inverse function? Oh, if we could just like write down the inverse to this function and use it, we'd be able to solve 5 to the x equals 7. It would be whatever the inverse function is of 5 to the x applied to 7. We'll talk about that next time. And the word for that inverse function is logarithm. That'll be next time. Nonetheless, we can still solve, nope, wrong page. So what I promised you next is just some more graphical observations. So simply just remembering, we have graph 2 to the x. We saw that its graph looks something like this. It gets really big as x grows. It gets really, really small when x gets negative. 2 to the negative x is the same as 1/2 to the x. Let's use that to graph something like 1/2 to the x. So it looks like this is going to be the same as 2 to the x, but with a minus sign in front of the x. What does that do to a graph? It flips it over the y-axis. It does the flip that resolves y values and makes x values negative. So let's do that. So now it's still going to go through this point 1, 0. Nope, 0, 1. But now this tail that dies off and goes to 0 will die off and go to 0 as x gets big. And then it will grow really fast when x is negative. That seem about sensible? And there's just like one weird exponent. 1 to the x is weird, in that it's not weird at all. What's 1 to the x always equal to? 1. No matter how many times you multiply 1 by itself, you always get 1. So 1 to the x is just 1. Is that an easy function to graph? And as long as we have access to things like Desmos, let's just check our intuition there. When b equals 2, yeah, we get the graph that we should get. When b equals 1/2. Does that look like the exact same graph again, but reflected over the x-axis? Did I say the wrong axis? Sounds right. B equals 1, do we just get a horizontal line of height 1? Nice. But there are lots of different choices of B we could use, right? Let's see what happens when that changes. So there we have powers of B when B is bigger than 1. It goes small. Can't have it go less than 0, so there's 0.9, 0.6, 0.5, 0.2, 0.1. Those seem to be behaving in roughly the described way. Yeah. So, whenever you see any power of x, any power of b, any b to the x, you know what the graph will look like. It will always pass through this point, 0, 1. Anything raised to the 0th power is always 1. If b happens to be bigger than 1, then you're going to multiply by something bigger than 1 a bunch of times as x gets big. Well, that'll get big. When you put negative powers of x in, well, you're going to divide a bunch of times. You'll get that horizontal asymptote, but it'll be as x goes to negative infinity only. If b is between 0 and 1, then again, it'll go through this point at 0, 1. If b is like 2/3, then multiplying by 2/3 a bunch of times will like make the whole result smaller. Dividing by 2/3 is the same as multiplying by 3/2. It'll get big when you do that. And 1 to the x is, of course, just the line y equals 1. All right, so now we have some graphs written down. Oh, I should be careful with my graphs. I drew that as if it had an x-intercept, didn't I? It doesn't. It doesn't have an x-intercept. It has a horizontal asymptote. Let's see what we can read off just from those graphs. What's the domain of any of these functions? Negative infinity to infinity. All real numbers. What about their range? And let's maybe just point at them one at a time. What's the range of that function? Let's just start at negative numbers. Are those in the range? Is 0 in the range? If I go a little bit above 0, is that in the range? So what's the range? Starts at 0. 0 to infinity, not including 0. So I guess I'm ready to write that. Is it the same for the next one? Does that have the same range? Yeah. And that makes sense. When you like reflect over the y-axis, you don't change any y values, you change the x values. What's the range of 1 to the x? Just 1? And whenever you see a set that's just a single number, it's the set containing only that number, which is indicated with set braces. So when b equals 1, that's like a weird case. So let's deal with the non-weird cases. When b is not equal to 1, what horizontal asymptotes do these exponentials have? They have a horizontal asymptote at y equals 0. But it's not like the same sort of horizontal asymptote as rational functions have. Rational functions have the same horizontal asymptote at either side, if they have a horizontal asymptote at all. So maybe I'll introduce a word that's, I think, a descriptive word, but not like a commonly used word for this, is a one-sided horizontal asymptote. Meaning that you see this asymptotic as x goes to positive infinity but not negative infinity, or as x goes to negative infinity but not positive. Cool. You feel pretty good? All right. So let's close with just some observations. These will be as much computations as anything else. There should be another page. Because there should be some graphing tricks. Yes, what did you do? All right. Well, I know what example I want to do next. Here's the next example that I want to talk about. Let's think about combining these functions together and what we can say about things like domains. So I think here's the first next example I want to do. Oh, okay, no, that's not what I wanted. Okay. Let's sketch a graph using transformations. Let's graph. Give me a base. 2. Give me a linear function. Good enough. Let's also multiply that 2 by -1 and add 1 to it. That look like something that we know how to graph? Yeah, I think so. Let's start by just remembering the order we're supposed to do things in. That -1 multiplied by a power of 2, what does that do to the graph? Let's go to the y-axis, x-axis, does the vertical step. And I really struggle with that, which is why I should always just say flips vertically. So that'll flip it over the x-axis. Flip over x-axis. That +1 next to an x, what will that do to the graph? Move it left by 1. What will that other +1 do? Up 1. All right, so let's do these one step at a time. Let's start with 2 to the x. Of the symbols written down there, which is the one you're supposed to deal with first? Because the order matters, right? Yeah. The thing done to the multiplied by the whole function first is the thing you should resolve first because of order of operations. So first, let's do that. There's the graph of -2 to the x. And I guess let's track that intercept at 0, -1. All right. What's the next step that I need to do? I need to move that left by 1 and up by 1. And maybe I'll start by just tracking this point. 0, -1. If I go left 1 and up 1, where am I? I hear a -1, 0. Let's also pay attention to that horizontal asymptote. I have a horizontal asymptote of y equals 0 right now. What happens when I move left 1 and up 1? Where is it now? 1. There's a horizontal asymptote over here at y equals 1. And now let's just shift the graph. The whole graph is going to go left 1, up 1. It needs to get to this horizontal asymptote. That intercept, I guess it's going to have some sort of y-intercept. And otherwise look exponential. Let's suppose that I want to label that y-intercept. How could we discover what that y-intercept is? Or just what is that y-intercept? How do you find a y-intercept? 0 for x. Put 0 in for x. Let's track that y-intercept by plugging x in 0 in for x. -2 to the 0 plus 1 plus 1. I find something we know how to compute. 0 plus 1 is 1. 2 to the 1 is 2. Then it becomes negative. Then you add 1, giving you negative 1. Which is, I think, exactly what you said. So I've got a y-intercept there at 0, negative 1. It happens to be the same y-intercept as before, but that's entirely coincidental. Nice. Groovy. Do you think from that you could now, like, tell me what the range of that new function is? Yeah, what is the range of that new function? Yeah. Yeah, but you put them in the opposite order. Negative infinity to 1. Cool. We feel pretty good? All right. Then starting next time, we have these nice one-to-one functions to study. Let's study their inverse. And I feel like I've probably gone over total so far by about 2 minutes, right? Yeah, so let's call it good. I'm now back to just on time. All right, so between now and next time, take a look at the homework for the day. Take a look maybe at the notes for next time, because logarithms can sometimes get a little bit technical feeling. That's the only way I was ever the base of the Stop the recording.